Professor, you're muted.
How's that? Better? Can you hear me now?
Yeah, we can hear you.
Thank you. Thank you for letting me know. All right. So last time we talked about the Rolle's theorem, which is, it pretty much says this. It's, if f of x is a continuous function on a closed interval and differentiable at all interior points x inside the open interval ab, then if we had two values at a and b that were equal, remember, it's a function's continuous and it's differentiable. Yes, it could be a constant function, which everything between there is true in the whole equation. The derivative is equal to 0 because it's a flat curve, a flat line. But if it's not, if this is true, that means that the function has to do something up and down somewhere inside there. If that's the case, then there's at least one value c where the slope is equal to 0, which means we have a vertex. So that's what Rolle's theorem tells us. Then from there, we moved on to the next theorem. Theorem 4. The mean value theorem, which we'll call MVT from here on out. The mean value theorem says this. Suppose you have a function f of x, and it's continuous. On some closed interval. And it's also differentiable at every x in the open interval. Now, let's look what this means. It's continuous. If it's continuous, that means the limit exists any point along the way. If it's differentiable, that means the derivative exists. That means it has a slope somewhere along the way. If all this stuff is true, then there is at least one value c in the open interval AB where, remember, it says it's differentiable. So there's at least one value c inside there where that derivative equals the slope of the function at 2 points. Here's our function f of x. Here's a. Here's b. So what this function tells us, the slope function, it's of the secant line. So the slope of that line connecting 2 points in that function is equal to some other point. This C point is an interior point inside the interval. So these are at the endpoints. There's some value C somewhere between there where the derivative, the tangent line to that line, is equal to the slope of the curve at those 2 points. Now, this is relating this back to chapter 2. Chapter 2, section 1. The f of b minus f of a over b minus a is what kind of slope? What kind of rate of change is it?
Average rate of change.
It's an average because it's a fraction, right? It's the average rate of change because it's a fraction. And we also learned that the derivative happens at 1 point. So that one is, it's an instantaneous rate of change. So this is what we're going to look at now. We're going to try to find the point where on that curve the average rate of change is equal to the instantaneous rate of change. And according to the mean value theorem, there has to be at least one value inside there where that's true. And that follows from Rolle's theorem. This follows from Rolle's theorem because if we had at point A and point B, we had 2 points. If we connected the slope between there, the line between there, the slope is equal to 0. Remember, at f of a equals f of b, the slope equals 0. Now, if that's true, then there's at least one value c where the slope is also 0, depending on where the vertices are. These two are telling us relatively the same thing. There's a Rolle's theorem, it did horizontal lines. And we also can use the Rolle's theorem and the mean value theorem to find the x-intercepts. So following this equation, we have the slope of that one we'll call these g, put us on a different function. So if we multiply both sides by the denominator, x minus a, then we have g of b minus g of a is equal to f of b minus f of a over b minus a times x minus a. You notice that b minus a and x minus a are not the same thing. So this one, this value here, instead of b, we can say it's f of x or g of x. This one goes from 2 points. This one is at any 1 point. So solving for g of x, we add g of a, and it's added this whole thing here. But because of, since we're looking at g here, we can say that these f of a's are the same value. Because we're looking for parallel lines. So because of this, we know that g of x, because any value x we pick, is equal to the function here, where a and b are defined. The only value we don't know is the x value. Let's look at an example here. Example 2. It says the function f of x equals x squared is continuous on 0 to 2. The way it says it's 0 is less than equal to x is less than equal to 2, but I rather just tell you it's an interval. And differentiable for any x. For any x in the open interval, or any x between 0 and 2. Okay, first off, is the function continuous? How do we check continuity? Yes, we know we have those 3 parts, but algebraically, how do we check for continuity? Are there any values of x that'll make the function undefined? For example, if we had 1 over x, what can x not equal?
0.
If we had square root of x cannot equal what? Any negative number. Any negative number. So that's what we're looking for algebraically. So x squared, does it have any x values that's not defined? No, it's continuous between negative infinity and positive infinity. So it's continuous on this closed interval. So can we pick, if we do the graph of this one, the graph of x squared looks like this. It's a parabola. All we want though is from 0 to 2. We want this closed interval. Is it differentiable inside there? Yes, because it's continuous. We want this value, and where's that? That value. So here's what I want you to do. Use the mean value theorem to find a value C in the closed interval, or inside the open interval, AB. Now, the reason the question doesn't say anything more than that, we know what the mean value theorem says. What does the mean value theorem tell us? It tells us that the derivative at C is equal to f of B minus f of A over B minus A. That's what the MVT tells us. So look at this. What do we have to do first? We have to find what first on the left side?
Derivative.
The derivative. So we have f of x is x squared. So we have to find the first derivative. which is 2x. On the other side, we have to find f of b, f of a, and b minus a. So what is a and what is b? A and b are our intervals. So what's our closed interval? What's the lowest on our closed interval? 0 and 2. So this is 0 and this is 2. So we have to find f of 2 minus f of 0 over 2 minus 0. F of 2, the function is x squared. So we have 2 squared minus 0 squared over 2 minus 0. So 2x is equal to 4 minus 0, 2 minus 0, 4 over 2. And solving for x, this is our value c. So what do we know that happens at c? Nope, that's not what I said. What does the mean value theorem tell us?
The average rate of change and instantaneous rate of change are equal to each other.
Which are what?
Continuous and differentiable.
No, the functions are continuous and differentiable. That the slope of the derivative, the instantaneous rate of change, equals the slope of the secant line. What is the slope of the secant line? What is the slope of the secant line? This is the secant, this is the slope, right? Let's work it out. We worked it all the way out. The slope, yes, you said 2, right? Yes. The slope is this one. So this is the x value. At x equals 1, the derivative will equal the same slope. The derivative is 2x. So since the derivative equals 2x, we have 2 times 1 is equal to 2. So that's what it tells us. So it proves to us that the instantaneous rate of change is equal to the average rate of change. This is the exact proof of it. Let's put another example. Okay. A car accelerates from 0 to from 0. Oh, it takes 8 seconds to go 352 feet. Its average velocity for the 8 seconds. Is 352 divided by 8 is equal to 44 feet per second. So what does the mean value theorem say about this? The mean value theorem says that, well, says that there exists at least one time t where during the acceleration the speedometer read exactly 44 feet per second. This was so a car accelerates from zero, from standing still, takes 8 seconds to go 352 feet. Its average velocity in those 8 seconds is, well, let's look at the graph of this thing. Time is always on the bottom, and the distance is the vertical. So it started at 0. One, two, three, four, 5, 6, 7, 8. So now as it accelerates, the distance gets further. Think about it. When you start running, is your distance covered per second interval the same as it is after you ran 4 or 5 seconds? If you're running a sprint. No, because whenever you start off, when you start off from 0, it takes time to build up your speed. So that's why your acceleration is like a curve. So according to the mean value theorem, that the distance traveled is f of 8 minus f of 0 over 8 minus 0. So how far was, after 8 seconds, you went how far? 352 feet. At 0, you didn't go anywhere. So this is where you get 352 over 8. That's where we got that from. That's the average velocity. Remember, what is velocity? The distance traveled, the change of distance over change of time. So the distance traveled is 352 over 8 seconds. So what this says is, because that's a tangent line, it's a secant line, that means there's a point, if we move this over, that there's a point somewhere in our graph where the slope is going to be equal. Okay, if the graph is accurate, of course. But this is what the mean value theorem tells us, is the average rate of change and the instantaneous rate of change have to be the same. And where it happens is you just match it wherever that is down here. So, and we can figure that out if we had the actual formula. So whatever value is down here, that's the time where the first derivative, the acceleration, is equal to 44 feet per second. That's what it tells us. The consequences of this. Because remember, what we're looking for is, when we did the Rolle's theorem, we found we're looking at what? We're looking for derivatives equal what? When we did Rolle's theorem.
The slope of the average rate of change.
No, so we wanted zero. Because Rolle's theorem was when f of A equals f of B. If f of A equals f of B, then the slope between those two lines is zero. Because that's where the whole section started. Is if this is true, then there has to be another point in which it's parallel. I spell corollary. Corollary 1 says this. Because, yeah, we can find A and B. That's the secant line. So what they're saying here is the secant line and the tangent line both have to have the same slopes. And that must exist. That has to exist if the function is continuous on a closed interval. So if the first derivative is equal to 0 at each point x on AB, then what has to be true? If the derivative is equal to 0 for every point inside the interval, what function has a 0 slope all the time? All lines are straight. Yes, there you go. A horizontal line. So if the function itself is a constant, if this is true for all x in AB. So that's a true statement, isn't it? If we look at any function, here's A, here's B. If that slope is equal to 0, then any point we have inside there is equal, the slope is also 0. So if that's the case, if we have a curve, and I don't care what the 2 points are, it doesn't have to be horizontal anymore. It doesn't have to be a 0 slope. So this slope equals this slope. So what we're looking at here now, what is the relationship between two functions that have identical derivatives? What that's asking is this. This is, since these aren't, are they the same functions? No, but they have the same derivatives. They have the same rate of change. So this is f of x, and this is going to be another function g of x. What do we know about f of x and g of x? Are they equal? In algebra, what do we call lines like this? They are parallel. So in algebra, what are the conditions for lines to be parallel? Well, two things have to be true. If
Same slope.
Right, if two lines are parallel, then they must have one same slope and what? If two lines are parallel, lines are bidirectional. How do you know if two lines are parallel versus the same line? They never intersect, true. That's the same slope. Good point. They never intersect. If they did intersect and they have the same slope, if they did intersect and they had the same slope, what kind of lines would they be?
Wouldn't they just be the same line?
Very good. If you had two lines that had the same slope, and the only way they can intersect is if they're the same line. That's the same line. But these are two lines that don't have the same, they don't intersect. So what has to be different if they don't intersect? Think about this. We had two lines and they're parallel. Okay, we know the slopes are equal. So this slope equals this slope. Slope of line 1 equals a slope of line 2.
They're y-intercepts?
What about them?
They're different.
Very good. That's what we're looking at here. The y-intercepts cannot be equal, because if the slopes are the same and the intercepts are the same, then they're the same line. So they have to be different by the y-intercepts. Now, in an equation, what are y-intercepts? How do they look in an equation?
First parts of the y and x are probably the same, and the b is different.
So yes, so now what's the characteristic of a b value? Yeah, you're right, because we had y equals mx plus b. What part of that equation is a y-intercept?
The b.
The b. That's the y-intercept. So what's the characteristic about b? What does it not have? It doesn't have an x. So the characteristic of a y-intercept in any equation, the y-intercept is always the what kind of term? How do
Constant?
we know? What's that?
Constant?
Yes, it's the constant. So the difference, if f of x and g of x have the same slope, the only way that they're different is if there's a constant difference. Look at this one. This is f of x. It's going through the origin. This is crossing at C. They have the same slope. That's how you can tell the two lines have the same slope. That's the characteristics. That's the relationship between the two functions that have the same derivatives. Because if we took f of x, took the derivative of it, what's the derivative of this side?
G of X.
And we have g prime of x. They have identical derivatives. So that means the only way these functions can be different is by a constant difference. That's what corollary 2 tells us. If f of x equals, or f prime of x equals g prime of x, at each point x in an open interval a b, then there exists a constant c such that f of x equals g of x plus c for all x inside the open interval AB. Now, does it matter what constant it is? Not really, but it does for the graph of it. For this one, could my constant be, could c equal -3 in this graph? The y-intercept is a constant, remember? Where's the y-intercept here? Is it positive or negative? So it can't be that one. So you can't just, in other words, what I'm saying here is you can't just throw a value c in there. There has to be a specific value c correlated to the rest of the information given. So let's look at an example here. Let's find the value of c. Find the function f of x whose derivative is sine x and whose graph passes through 0, 2. So we have to find an f of x whose derivative is equal to sine x. So what function does that satisfy? Negative cosine. What's interesting is what you have just done without realizing it is you've just done the integral of this function. You've gone backwards. You're going backwards, right? But we'll cover more of that in chapter 5. But now we have this, but the graph has to go through 0.02. Because remember, in order for these functions to be equal, what has to be true is the function has to have a constant. And it has to go through 0, too. So what is the value of C? Do you
One,
know what f(x) is? What's the value of f(x)? That's the y value, which is 2. What is my value for x? X is 0. What is cosine of 0? Is 1. Solve for C. Add 1 to both sides. C is equal to 3. So that tells me my function is negative cosine x plus C, where C, negative cosine of x plus 3. That's the function I'm looking for with that specific information. Any questions so far? Everybody follow that? So if you're looking for this information, if I give you the derivative, you have to find me the function where it came from, and then add a c to it. Here's the function that I know the derivative of it is sine x. Once you find that, then we add c to it and then plug in this point 0, 2 is called the initial condition. With all this other stuff, we know that it has to go through 0, 2 as well. This also works with logarithms. For example, if f of x is equal to, which one we use? ln bx. What's the derivative of fn bx?
one over x.
Why is that?
Because the b would be cancelled out over 1 over x, and you find the derivative of u.
Well, yeah, this is the operation, so it's 1 over bx. That's the derivative of ln times the derivative of this is my u value. So if u is equal to bx, u prime is b. The b's cancel, so because any value, any equation, f of x ln bx, it has the same slope as ln x. How are they related? What's the derivative of ln x? G prime is equal to 1 over x. They have the same slope. So how are they related? Or f of x is equal to g of x plus c. Everybody remember the exponential properties? We're talking about exponents first. This goes for any exponential equation. When you multiply the same base, different exponents, you add the exponents. Whenever you divide same base, different exponents, it's subtraction, because when you divide, it makes things smaller. When you have a power to a power, exponential power to a power, that's when you multiply them. A negative exponent simply means you move that to the other side of the dividing line and drop the negative. Is there any limitations what x can be? Not really. So it also works if x is equal to e. All of these work the same way. E to the power n e to the m, e to the m, e n minus m. So the reason why I say this is because what's the inverse of e? What does ln x equal? So if let's say that equals some number y. So what does x equal? Ln is log base e. That's where ln comes from. Take the base, move it over here, so x is equal to e to the power y. So the inverse of e is ln. So it means if one of them is continuous, the other is continuous. If one's differentiable, the other one's differentiable. All right.